Hello everyone, my name is H2OLyon. I am assistant professor at Lyon, Laboratory Field Mechanics and Acoustics. And we're very pleased to receive George for 3 months. The EUR H2OLyon is welcoming him in the name of, we are welcoming him in the name of the H2O. Who is we? So the Laboratory of Field Mechanics and INRAE Lyon. And George came within different research projects to work with us. George is a full professor at the University of Iowa, working on using CFD to apply to any river flows that he will show today. So he's among the advanced researchers working in CFD to understand more the physics of watercourses in general. So I will let George, and we asked George to give a seminar especially dedicated towards ecology. It's not his first talk during his stay in Lyon. So this one is really dedicated towards ecology, how CFD can be useful for ecologists, river ecologists. So George, if you may.
Okay, so thank you very much for the introduction, and thank you very much to everybody at the H2O school who made possible my trip to France, which I'm spending all the summer in Lyon working with different groups. So it's a pleasure for me to be here. And what I'm going to try to do today is to give you some examples of some projects I was involved over the years, which have an ecological component. Myself, by training, I'm a civil engineer. I do not know much about ecology except some generalities, but sometimes I got basically to work with some fish ecologists and with other people who basically have a much sounder background in ecology. And we are very much interested in understanding mixing processes, transport processes in both rivers and in lakes, and how basically what we learn from these three-dimensional numerical simulations, in some cases simulations which are also capturing the large-scale turbulence, how this knowledge can be applied toward ecological modeling or to understand some phenomena which are of interest to river ecologists and to lake ecology in many. So, as you know, many ecological and biological models need data, hydrodynamics data, and also in some cases some data on transported variables like nutrients or phytoplankton. And these are needed in many ecological models, and I basically listed here some which have to do with the examples I'm going to present you afterwards. So for example, in the case of mussel population models, where we want to predict how the mussel bed is going to evolve over a large period of time in a river, we need some data on the velocity flow field, on the bed shear stresses. In the case of models which are trying to predict the trajectory of the fish, let's say upstream of a power dam, we need in fact very detailed three-dimensional information on the velocity field. Of course, in many cases, the usual approach is to obtain this hydrodynamics information using field experiments or laboratory experiments, and this is of course a valid approach. But in some cases, this information is basically provided or is available only at relatively large spatial and temporal scales, especially the spatial scale is the main limitation. So one way to basically get data which is very fine in space is via three-dimensional numerical simulations. So in my research, I'm mostly using three-dimensional numerical simulation, and in particular the ones which are capturing the large-scale turbulence, to study flow and transport processes in rivers and lakes at both the large scale and, I think very importantly for this audience, also at the field scale. What are the goals? What are we going to do with this data? So first of all, these numerical simulations can provide relevant information for scientists working in river and lake ecology, sustainability, and river management at the level of better understanding some ecological processes. And in some cases, this data provides the input toward ecological models. And I'm going to basically, the first example I'm going to discuss is that where we are using the hydrodynamics data to be able to forecast the trajectory of the fish in the forebay of a hydraulic dam. Couple of words on the role of numerical modeling in aquatic physics research. So numerical simulations generally are used for two purposes. The main one is to investigate the physics of the flows and transport processes in rivers, lakes, reservoirs over a wide range of scales. The other one is to use them as a tool to help in management and decision making. So the first step to be able to use them as a design tool is to make sure that the data which we get from this numerical simulation is accurate. So this is basically a first step, which is very, very important. So we have to validate using experimental data either from lab or from the field. And nowadays, more and more using remote sensing observations. Okay. So once basically we validated how we can use this numerical simulation as a tool to manage rivers and lakes. Again, there are a couple of ideas. So we can simulate all sorts of hypothetical scenarios. What if we have a pollutant which is spreading into a river, how that is going to affect the life of the fish or of vegetation, how we can optimize the design of hydraulic structure which are introduced in the forebay of the hydropower dam, such that we can keep the fish away from the intakes. Okay, this is a very important problem, especially in the Pacific Northwest of the US. And then other class of applications are related to developing strategies which lead to an engineering sustainable design. And two examples of particular importance are the maintaining and restoring ecological habitats, let's say for freshwater mussels, this is going to be my second example, or developing strategies to increase the fish population in rivers. Okay, so let me start with the first example. So this is work which was conducted really about 20 years ago. And it had to do with a large problem on the Columbia and Snake rivers in the Pacific Northwest of the US, related to having several very large fish kill events. And those fish kill events were mainly triggered by very large temperature and also very high solar radiation. So what happens is that during a very hot summertime, you have, this is also the season where the juvenile salmonids are basically migrating downstream. And the issue is that some of these salmonids, or some of this fish is basically injected in, basically going toward the powerhouse units, and from there into the intake, typically the fish is 10–15%, but also there are lots of problems related to the health of the fish. So in order to basically minimize the number of fish which is going through the intakes, there are basically two ways of doing that. So they have a certain number of what they call fish screens, where they are trying to retain the fish and then to divert this fish toward a collection channel, okay? But even in this case, what happens is that in those very hot days, there is some hot water which is recirculating close to the two shores, and this hot water can be injected into the powerhouse units, and then the fish will experience a high temperature, and then when it is basically going through the fish pathway, downstream is going to go into colder water. And this happens quite fast, so the temperature gradient is going to be very high. And again, this is going to result in endangering the life and the health of the fish, okay? So this is basically the main problem here. And the question which the US Army Corps of Engineers, which is the US agency in charge of operating these dams, they are basically asking what can we do structurally and also in terms of operating the powerhouse units and the dam in order to minimize having fish being exposed to these high temperatures, okay? So this is basically where we were asked to help. So what we created is a 3D model of the forebay. I think it goes for something like about 10 kilometers. We basically including all the 14 powerhouse units, the 22 spillways, and then there are a number of hydraulic structures, some of them related to the fish, some of them to navigation, which are also part of the hydropower dam. Okay, so you can see here a cross section. You can see how the bathymetry looks like. It's pretty irregular. And basically, the important part for us are the powerhouse units situated here, and there are 14 of them, and this shows one of them. You see there are 3 gate wells, and inside of the gate wells, there are 2 screens which are called VBS and ESBS. These are basically the screens which should retain most of the fish approaching the intakes, and from there to the fish orifices, the fish are collecting toward a collection channel, and from there they will go toward the fishway passage. Okay, so the Corps basically was interested in using or in basically constructing and installing a fish barrier. So barrier will basically be like a wall from the fish surface up to some distance away from the bed, and the role of this fish barrier will be to retain most of the surface water from this region where the flow is recirculating, because this is the water which is the warmest, and hopefully not much of this water is going to go into the powerhouse units. The other question the Corps is asking, with this barrier in place still, how they should operate the powerhouse units and the spillways in such a way in which they will minimize the detrimental effect on the fish. Okay, so basically they provided us with all sorts of scenarios in terms of operating the dam, in terms of the placement, the angle, the length, the height of this barrier, and they asked us to identify what will be the best solution. So in order to be able to answer these questions, because again the system is very dynamic, the water is basically warming up during the day, and then it's basically cooling during the nighttime, we need to have a model which can simulate the temperature related to both the changes in the air temperature, which is shown here, and the solar radiation, which in fact is the most important component. So you can see how the red regions, which are the high temperature, are going to basically start forming the 2, especially here, and then the water is basically drawn into the powerhouse unit. So this is a simulation in which we didn't have any of those flow training devices or fish training devices, but basically this is the kind of model we provided to the course, and then we ran all those simulations with different scenarios, and based on that, the Corps basically decided where to put the barrier at what angle, and and basically this barrier is now basically in place. Okay, so this is a structure which the Corps already implemented. So another part of this project is based on steady state simulation, and this has to do with connecting the hydrodynamic results in terms of the velocity field in the forebay of the power of the dam with a model, an ecological model, which basically tries to forecast the trajectory of the fish. Okay, so we are going to use a steady state simulation. We don't care about the temperature at this point, and we are going to release fish upstream of the dam, and we are going to basically again try to have different scenarios in terms of how we are going to operate the dam, and see what scenario will lead to the fewest number of fish going through the intakes. Okay, so in order to do that, this was work done by Andy Goodwin, both in Cornell University through his PhD, and then after that he's still working for the US Army Corps of Engineers together with John Nestler, who is a fish biologist, and they came up with this Eulerian Lagrangian eigenvalue method, this is how they call it, which is an ecological model which can predict the trajectory of the fish responding to abiotic, and in this case will be hydrodynamic stimuli. Okay, so the idea is relatively simple. We have the pre-calculated velocity field in the whole domain, so that basically will be used to know what will be the velocity of the water at the current position of the fish. But then basically the fish will decide how to go, because the fish is not a passive particle, depending on some things which happens close to it. Okay, so they are going to they define what they call an ovoid. Okay, and this is the region around this is the region surrounding the fish where the fish basically is aware of what happens. So for example, the fish responds not only to the velocity, but especially to the strain, which is just the velocity gradient. Okay, so the strain, the distance from the fish surface, its orientation from the previous time step are basically the main variables based on which the fish is going to decide what's going to do at the next time step. The time step is of the order of 1 second, because typically the fish makes decisions at every 2 seconds, at least for the salmon. Okay, and they are using all sorts of sophisticated algorithms, typically some game theory. So each basically abiotic stimuli has associated with it a probability, and they have an equation how this probability is going to evolve in time to know the fish is going to make this decision based on this stimuli, the other stimuli, etc., etc. So it's becoming quite complicated. But at the end of the day, you are going to see in these examples, which I'm going to show you, this approach can realistically represent a fish movement with an aquatic system containing all those hydraulic structures which I showed to you before. So this is another dam in the Pacific Northwest, is the Lower Granite Dam. You can see here that it has all these type of barriers and trash booms and all sorts of other hydraulic structures. It has a removable spillways which goes around the powerhouses. And this is an example of a fish trajectory computed using the fish surrogate model. And you can see that the trajectory doesn't have anything to do with the one associated, let's say, with a passive particle. And you can see this is a view of one trajectory from above. And this is a lateral view of the trajectory. You can see that the fish is also going up and down quite a bit. And once it's approaching the screens just in front of the powerhouses, you can see that it starts basically kind of going in circles. Okay. And this is just an example to show the difference between the case in which the model is cut off and the fish is just a passive particle. So the trajectories will be quite, there's some relatively well-defined lines. And you can see the difference in which basically the ecological model is turned on and the fish basically behaves as a fish based on on a certain number of constraints, which tells the fish how they are going to move at each time step. So the problem now is how they are going to validate such a model. So what they did, they basically do acoustic tagging. So basically they take some fish and they basically introduce an acoustic sensor. And then with a helicopter, basically they release a certain number of fish with the powerhouse discharges and the spillways discharge is constant. And then basically from the plane, they are basically recording all these trajectories. And then basically what they are doing percentages. What is the percentages of fish for that operation which went through the spillways? Which is the percentage that went into the powerhouse units, and from there it went into the fish collection channel, or which is the percentage of the fish that went into through the turbines. Okay. And basically they did this with the same dam with different operating conditions, and then they did it at 6 different dams. So they have something like 30 scenarios, 30 validating scenarios, and based on this, they were able to calibrate all the constants in their model. And in fact, they are able to predict for one species, or for salmonite, you don't have to recalibrate it even if you go to a different dam. If you want to basically study trout, then you have to recalibrate your model. Okay, so that's the trick. So now let me show you a movie. I'm going to show you just 1 minute.
Lower Granite Dam on the scenic Snake River in Washington State is one of many hydroelectric projects worldwide where the passage of migrating juvenile fish is an important environmental issue. At Lower Granite and other U.S. Army Corps of Engineer dams in the Pacific Northwest, research is now underway to develop better methods for passing juvenile salmon around the dams to increase the number making it to the ocean, where they will mature and return as adults. To help in this effort, the Corps has developed an analysis and modeling technology called the numerical fish surrogate, which is used to mathematically decode the 3D movement behavior patterns of individual fish responding to hydrodynamics, water quality, and other stimuli in their aquatic environments. At Lower Granite Dam, the technology couples a sophisticated fish swim path selection model to a 3D computational fluid dynamics model. Complex movement behavior patterns of electronically tagged individual juvenile salmon are translated into a mathematical description of behavior. The numerical fish surrogate technology allows design engineers to forecast the impact of future structures and dam operations on the movement and passage response of juvenile salmon in a virtual reality environment. Structures can then be modified or eliminated in the early stages of project planning, reducing costs and dramatically minimizing the environmental impact on migrating fish populations. The numerical fish surrogate can forecast which way fish may swim when these man-made objects are added to their environment, providing engineers a new tool for designing future structures.
The second topic. So in the second topic, I would like to talk to you a little bit about flow over mussel beds in rivers. So first of all, why are we interested in mussels? They are natural filters and they play several important ecological roles, like they are converting nutrients from the plankton into proteins, which are then used by fish and invertebrates. They are also clarifying the water. Why is that? Because they have an inherent siphon. They are basically getting water which is rich in plankton, and then they are using the plankton more or less as food. And then they, through their excurrent siphon, they are basically eliminating water which is low in phytoplankton, and that basically increases the clarity of the water. They are also redistributing the oxygen and the nutrient in the soil. Now there are nowadays lots of problems with declining mussel habitat in rivers, and there are two main sources. One is something which we don't have, we are not working on that. We have some invasive mussel species, but the other one is something which we can address through modeling, through CFD modeling, and this is related to the loss of habitat, because most of the loss of habitat occurs when mussels are dislocated from the substrate. Okay, so that typically happens when the discharges in the river are high. So typically that happens at flood conditions. And in order to predict if a mussel is going to be dislocated from the river, what you need to know, the most important variable you need to know from numerical simulation is going to be the force acting on the protruding part of the mussel shell. Okay, so this is something which we can calculate quite easily using our numerical model. Then there is lots of interest in the distribution of the phytoplankton over the river which contains mussel beds. Why is that? Because mussels basically feed themselves on phytoplankton. So as we go downstream, the concentration of phytoplankton is going to decrease, especially close to the bed. Plus, there may be other organisms in the water which also use phytoplankton as food, basically. Okay, so we are going to basically first look at flow structure, mussel stability, and eventually we can also talk a little bit about local scour mechanism around the mussel, which can also contribute to the mussel being dislocated from the substrate. And in the second part, I'm going to talk about the distribution of the phytoplankton concentration and the associated boundary layer. So first of all, what are the main flow and geometrical parameters which are important for this problem? At the mussel individual scale, it's important to know what is the approach velocity u. It's important to know what is the angle of attack, so the angle between the approaching flow velocity and the main axis of the mussel, okay, which is partially barrel. We also need to, it's very important to know the protrusion height h, so basically the distance over the average position of the bed over which the mussel is situated. And also what is the filtering flow rate. So basically, as I already mentioned, the mussel has an inherent and excurrent siphon. The discharges to the two siphons are equal. The openings are not equal. So the inhaling velocity and the excurrent velocity are not equal. But typically in the literature, instead of using the filtering discharge, people are using this filter and velocity ratio, VR, which is defined as the ratio between the velocity in the excurrent siphon divided by the velocity in the main channel. And when we are talking about the mussel beds, the other very important parameter, geometrical parameter, is the mussel bed population density. How many mussels do we have in 1 square meter? So in terms of how we are going to build our CFD model, we basically get a muscle. Then basically we do a tomography of the two shells. We then get that information in AutoCAD. We separate the two shells. Then we are going to get into our model the incurrent and the excurrent siphons. And generally, we are also going to put one pipe linking the excurrent siphon, okay, such that we can get a very physically realistic flow field as the fluid from the excurrent muscle, from the excurrent siphon enters the domain. So this is basically how it shows. We basically put it on a flatbed here. We first mesh the surfaces, and then basically we do a volume mesh where we have a very fine mesh near the muscle, and then the mesh is refined as we go at larger distances from the muscle. So we do exactly the same thing in the case of a muscle bed. So here we have a muscle bed containing a couple of hundred muscles, and then what we are interested in, as I already mentioned, is to know what are the forces acting on the emerged part of each muscle. And these forces are going to be different for the different muscles inside of the muscle bed. And the main contribution is going to come from the pressure. Okay, so you can see that always the pressure is higher on the part on which the incoming flow impinges onto the muscle, and the pressure values are smaller at the back of the muscle where the flow recirculates. And as a result of this pressure difference, this is going to be the main component of the streamwise and span-wise drag forces. So here, basically, we are showing how the drag force on the individual muscles represented by these points is basically varying with the distance from the leading edge of the muscle bed. So we have a muscle bed which is basically 100 times the average height of the muscle which we use in our numerical simulation. And you can see a trend. So there is a general trend where there is first a decay in the drag force, and then the drag force more or less becomes constant. However, there are large differences between muscles situated at more or less the same streamwise distance. Why is that? Because some muscles are situated in the wake, like this muscle is situated behind this muscle, so its drag force is going to be relatively small, even though it's situated close to the leading edge, while other muscles at larger streamwise distances are situated quite far from muscles in front of them, so they are going to experience larger drag forces. So then what we can do in order to get some more generic trends, we can basically do what we call a window average. So we can basically take a region and do one more spatial average, and then we're going to get curves which look like this, where you can basically get only one line for one test case. Let's say one case which has a given muscle density, a given velocity, filtering velocity ratio, and a given protruding height of the muscle. And you can clearly see here that there is a regime, a first regime, which is characterized by a close to linear decay of the drag force, and then it goes more or less constant. And this is true for relatively high muscle bed densities, 55 and 100, but when we go to a density of only 10 muscles per meter square, you can see that the drag force is more or less a constant. Okay, why is that? Because each muscle behaves as an isolated muscle, the flow modifies as it goes over the muscle, it recovers, and then when it goes to the next muscle, it's like the, the flow which the first muscle in the series is going to experiment. So basically from the CFD, we can get the drag force acting on the protruding part of the muscle. The thing which is missing here in order to say if the muscle will be dislocated from the substrate or not, is basically, you can get it only from experiments. So you have to do experiments with only one isolated muscle. You take a muscle of a certain species, you basically do experiments with different protruding levels, with different substrates. Okay, the substrate type also matters because the muscle really tries to anchor itself in the substrate. It also has a leg. Okay, and then you have to measure, you have to increase the discharge in the channel little by little, and you have to determine the discharge at which the dislocation occurs. And then from a CFD model of only one muscle, you can get the drag force for that case. And then using this correlation, you can basically make a prediction based on the drag force of each muscle in your numerical model, if muscle dislocation is going to occur or not. So what we did next was to basically focus only on the downstream part, in which basically the drag force is relatively independent on the position of the muscle inside of the muscle bed. So what we did was to do numerical simulation in which the flow is periodic in the streamwise direction. Okay, so the flow here and here is the same. So this corresponds to what we call a fully developed flow. Okay, and in this case, we added one more parameter of interest, which is the roughness of the bed. So, for example, here we took a scan of a gravel bed, okay, and basically we put the muscle on a gravel bed and we compare these results when the muscles are basically put on a smooth bed. Okay, and again, the muscle species is a little bit different. These are a little bit more streamlined muscles, but in terms of results here, we can really have basically for each test case, we can get only one value of the drag force. Another important parameter is the fluctuations of the drag force, because muscle can be dislocated even if the mean force is maybe not very high, but if the fluctuations are very high, then the muscle can be dislocated. So we are looking at the variation of the drag force, the mean drag force with increasing muscle bed density, and of the RMS fluctuations, or the root mean square fluctuations. And here we have the drag forces in the span-wise direction. And you can see that as we increase the muscle density, there is a decay in the streamwise drag force, which is totally expected, because as muscles get closer and closer to each other, they are going to be situated in the wake of other muscles, so the drag forces are going to be relatively small. But what is interesting is for the high muscle densities, where muscles are not really touching each other, but close to that, you can see that the streamwise and span-wise drag force are kind of, about of the same order, and the span-wise RMS fluctuations are even higher than the mean forces. In terms of the effect of the bed friction, the effect is relatively small. There is a little bit of decay of the streamwise and spine-wise drag forces with increasing roughness of the bed, but the effect is relatively negligible. Now, in the second part, I wanted to tell you how we can use data from our numerical simulations to make some overall predictions on how the concentration of phytoplankton is going to vary over the muscle bed. Okay, so as already mentioned, the concentration of phytoplankton is important because through the fact that the muscles are retaining the phytoplankton and they are releasing clear water, they are increasing water clarity. So what we are going to do in our numerical simulation is also something which was done in experiments. So there are several papers from Stanford, which they didn't look at freshwater mussels, but rather at clams in coastal regions. So rather than having in reality, we have the concentration of phytoplankton, which is high in the incoming channel, and then the concentration of phytoplankton in the excurrent current will be equal to 0. In our numerical model, we are basically doing the opposite. We are considering that the water reaching phytoplankton has a concentration of 0, and the concentration of the water which has no phytoplankton is equal to C0. Okay, so it's totally equivalent, but it's much easier to work with this. And basically, this is how, if you basically, I take a cross section, this is how the phytoplankton is distributed over the bed. So you can see here some mussels. There are some jets containing this filter water, which are coming. So the red corresponds to filter water and the blue corresponds to water rich in phytoplankton. So then what we can do a width averaging and also time averaging. And when we do the width averaging, we are not integrating through the interior of the muscle such that we can get something which looks like a two-dimensional flow field. And Z over H equal to 1 corresponds to the top of the muscles where the incurrent and excurrent cycles are situated. And I'm going to denote with Cmax the concentration along this line, which is also the maximum concentration for each vertical profile. So you can see that you have a first region which basically contains this blue water, which is basically water high with a high level of phytoplankton, the same as the one in the incoming water upstream of the muscle bed. But then at a certain streamwise location, this concentration boundary layer is going to hit the free surface, which means that up to the free surface, I'm going to have water which has a lower concentration of phytoplankton compared to the initial concentration in the water. Okay, we would like to characterize the growth of this boundary layer, okay? And we also would like to characterize the variation of Cmax, because if we know those things, we should be able to, given a certain river ridge, given a certain discharge, a certain height of the muscle, a certain muscle density, we should be able to say how much should be the concentration as a function of space, okay? So in order to do that, we are looking here at the width of the boundary layer and also the variation of the maximum concentration along the streamwise direction. So you can see, for example, that if we are varying the protrusion length of the muscle, the Cmax basically is not affected. But if we increasing the density of the muscle bed, Cmax increases. This is expected because you have more muscle per square area. But you can also see that the rate of increase of Cmax in the streamwise direction is also increasing monotonically with increasing muscle density. So in order to be able to use this information and predict C as a function of space in your channel, it would be nice if we can show another property of the concentration inside of this boundary layer. And this is self-similarity, meaning what? Meaning that the profiles at each station, at each streamwise location will be different. But the question is, can we non-dimensionalize those profiles in such a way that all the profiles are going to collapse in only one profile? So if we basically represent C non-dimensionalized by Cmax, okay, so this is why it's so important to know how Cmax varies. And we basically put the non-dimensional distance between this point, let's say we want to see at this point, and the top of the muscles. This will be Z minus ZC divided by the thickness of this layer, okay, delta C minus ZC. Then you can see that all the concentration profiles are basically collapsing into only one profile. And this is very important because then for each case, for each muscle density, velocity ratio, and protrusion rate, we are going to get only one curve showing us the non-dimensional concentration inside of the concentration boundary layer. And you can see that there are two regions. There is a region where basically the decay of the concentration is relatively linear, and there is a second region where the decay of the concentration is exponential, but the constant in the exponential decay is, for example, a function of the muscle density. So we can basically calculate all these coefficients for the exponential, for the linear function, and we should be able, with minimum information, to tell you at this point, at this distance from the start of the muscle bed and at this distance from the bed, the concentration of phytoplankton is going to be this value. Okay. Another variable which is of interest for ecologists working in rivers is basically what's called the refiltration rate, which characterizes the capacity of the muscle to filter water in the system. This is something which can be calculated with a very simple formula. It's basically the mean concentration in the incurrent siphon divided by the mean concentration in the excurrent siphon. There will be C equal to 1 in our the way we set up the numerical simulation. So you can see that for the muscle situated at the leading edge of the muscle bed, where basically there is no filter water hitting them, this CI is equal to 0, so then the refiltration rate is equal to 0. But as we go further downstream, the refiltration rate increases, and you can basically propose a simplified model, which basically has a constant multiplied by 1 minus an exponential function, and then you can get the value of these two model constant as a function again of muscle density, of the filtration velocity, of the protrusion height, and so on. So this is basically, again, how we can use these numerical simulations in order to characterize some variables which are important for, in order to characterize the stability of the muscle beds and the distribution of the phytoplankton. The third application I wanted to talk to you about is bioconvection in lakes. So so first of all, what do we mean by bioconvection? So bioconvection relates to the generation of large-scale motions by swimming organisms. In this case, the swimming organisms are going to be bacteria. Okay, so bacteria can basically create mixing by two ways. So they basically move like a fish moves, and they generate vortices of eddies. The problem is that those vortices and eddies are very small, so they are going to basically be dissipated very soon, or by this generating this large-scale motion in the form of bioconvection. So in order to have bioconvection, you need two conditions, you need to have an organism which is swimming upwards. Typically, bacteria swim toward light, so they swim toward the free surface, and also this has to develop this swimming in a stratified environment. So what happens is that as bacteria try to move up, they are going to start agglomerating around a certain location, and they are going to increase and increase more the density of the water, because the water we have a component coming from salinity or from temperature, and a component related to the concentration of the bacteria at that location. And then you are going to have heavy water over lighter water, and this is unstable, and this is going to generate some convective plumes, and eventually this is going to generate some large-scale motions. So in the case of bacteria, and this is a case in which we were looking in a lake, in an Alpine lake in Switzerland, you basically have bacteria accumulating in a certain layer, typically about 12 meters from the free surface. Typically, initially, the bacteria is uniformly distributed inside of this layer. You have a stratification which is imposed by pretty much of a linear salinity gradient, okay? And then very important, you have the distribution of the concentration of dissolved oxygen. And this concentration is about constant up to some distance, close to 12 meters, where the concentration decays very fast. So the problem with bacteria is that they try to swim upwards, but once they basically start getting into a region which has dissolved oxygen, this is very toxic for them, so they cannot swim above that level. So what's going to happen is that bacteria are going to accumulate around just beneath the oxyline level, and they are going to accumulate until basically the water becomes heavier than the water beneath them. And as a result of that, you are going to basically generate very large scale, very large recirculatory motions. Let's see. Oh, fine. So you can see this basically a stable stratification which generate these mushrooms like eddies, and the bottom part also is moving up and up and up because of the upward swing velocity. And at a certain point, basically, we get only one layer, and this layer from here on is going to start expanding and expanding. And you can see these large recirculatory cell motions, which are basically thousands or more than several orders of magnitude larger than the bacteria. And this is a very efficient mechanism for mixing in lakes. So because I'm out of time, let me just go directly to very brief conclusion. So basically what we were trying to show in this talk is that three-dimensional data from numerical simulation can be used to understand the flow physics and the physics of transport processes, which can be of relevance to ecologists working on fish, working on mussel beds, or working on habitat in lakes. Also, in terms of the fish project, CFD was able to provide the data which is needed in order for the ecological model to be run. So it provided the spatial distribution of the velocity inside of the river. And I think a main direction for future work is to try to have codes which basically they integrate the hydrodynamics, the transport part, and the ecological model. So at this point, you have seen with that fish surrogate model, we were basically first doing the numerical simulation for the water velocities, and then that was providing as a input data for the ecological model. It wasn't basically done in a couple of ways. And I think nowadays we should be able to do this kind of simulations, and we can basically go from a velocity field which is steady to a velocity field calculated which basically resolves the turbulence, so basically it's unsteady, and that should result in even more realistic trajectories of the fish, for example. So thank you very much for your attention.